Uh, hmm. So we will start with magnetic effects. Have you seen the magnet in your real life? This basic question.
Yes, sir.
So how, how and what does a magnet look like?
Bar shape.
Yeah, shape of magnet. How the magnet look like? What is magnet? First question. Magnet. What is magnet? This is very famous story. Okay, there is one area called Magnesia, or somewhere in Magnesia or something in Europe. Okay, I will start with a short story. There was a mountain in some area. It's a real story. Okay, everyone is getting my voice.
Yes, sir.
Okay, there was a area in somewhere in Europe, or there was a mountain. Okay, so that mountain was called Sacred Mountain. Okay, sacred. So what was a story about that mountain? That people used to go there, but they used to remove their shoes. They don't take their shoes to the on the top of the mountain. They used to remove their shoes. Remove their shoes. Sometimes you have seen that elderly people use sticks like this type of sticks. This type of sticks. Have you seen any? Back in your home or village, elderly people using a stick. Everyone has seen.
Yes, sir. Yes, sir.
And at the end of the stick, there used to be some metallic cup. Have you seen like metallic
Yes.
cup? Yeah.
Yes, sir.
In older age, even with the shoe, the lower part of shoe were used, and it was sometime keeping uh, snails to keep it intact with ribbons or something. Okay, getting the story?
Yes, sir. Yes, sir.
Okay. So whenever people used to climb over the mountain, so what happened? These metals at the top and the nut on the bottom of their shoes, they get attracted with the mountains. Okay. So when you are climbing and someone is holding your leg or holding your stick, what you will feel? On the plane, it is okay, but whenever as you climb on the mountain, you see that someone is holding your a stick or holding your leg. So what you will feel? How you will feel?
Scared.
You will get scared, right?
Yes, sir.
Everyone will get scared. So it was time passing and passing. People were saying, "Oh, that is a sacred mountain. You shouldn't climb over there." If people climb, they used to remove their shoes. Okay, they used to walk on the barefoot. If you are barefoot, nothing happens. Clear? If you are carrying your stick, if you are throwing your stick, you can climb it. So people says, okay, so it is the sacred mountain, and the gods of the mountain doesn't want people to carry their shoes or that sticks. The story was people didn't figure it out. What is the reason? Okay, can you tell me what could be the reason? Can you guess what could be the reason?
Sir, can you please repeat the question?
My question was, you got the story of the shoe and a stick.
Yes, sir.
Okay, so when people were climbing on the mountains, they were getting the force, or they were realizing that someone is holding their stick, someone is holding their shoe. So it was difficult for them to climb over there, right? So
Sir.
they thought that is a sacred mountain, and we shouldn't climb over there. The goddess or whatever it is, they don't want us to climb with our stick or shoe. So they started climbing over that mountain barefoot or without a stick. So whenever they go barefoot, there is no any uh, what can I say, obstruction or limitations from mountain surface. So they started climbing on the mountain barefoot. So can you tell me what could be the reason behind that?
Magnetic field.
Magnetic properties of that rocks. Magnetic properties of rocks. Magnetic property of rock. So from this story, we come to know that the magnets are the natural materials. Okay, so we can say that one, magnets are natural materials. Natural materials. Clear? And second thing is that it is man-made as well. Man-made as well. So can you tell me, have you ever seen the man-made magnets? Have you ever seen the man-made magnets? Question is open to everyone. If you think, you can open your videos camera. Okay. There was, I'm not able to see who is there and who left.
Yes, sir.
Have so where do you see the man-made magnet? Only two left. Who left the class? I think someone left the class, right?
Suresh left the classroom.
Okay. So I think his network was not good. Okay. So these are the man-made magnet and man-made magnet. Where do you see? Where do we see man-made magnet?
The horseshoe magnet.
Horse, horseshoe. Horse. You say this? These are the natural materials. Okay, we use natural materials. Like that, na? Like that magnet. These are the natural magnets, right? In man-made, you might have seen that conducting metal, and we used to wound the wire over it. And pass the current over it. Okay, this type of a structure is, and when we will pass the electricity, because of mutual induction, electromagnetic induction, the magnetic field will arise, and this coil will get magnetized. This is purely electromagnetic induction phenomena. Clear? If you will see the generators, have you seen generators? The structure of it. There is a inner part and outer parts. You see that there are copper woundings, copper woundings, and that copper woundings makes magnetic fields. Okay, and that magnetic field being used to rotate the axle, another inner part. In that case, we get the electricity in our homes because of magnetic induction. Clear? So everything come understandable till this point?
Yes, sir.
Any doubt? This is a story. What could be the doubt? Okay. So we will study one more phenomena of the natural magnets, and then we'll come back to the man-made later. So let me see. A magnet, if this is magnet, it has two poles. One is called north and another is called south. Clear?
Yes, sir.
So if we bring another magnet, say this is north and this is south. Now we bring a hammer and strike it. Just this is a hammer, and we are striking it. We are breaking it into two parts. So what will happen? Suppose we break it from this part. So now how the north and south pole will rearrange itself? So now it will behave as separate two magnets, north-south, north-south. Got the point?
Yes, sir.
Sorry?
Got the point, sir.
Okay. So if further we break, again it will be north and south. North and south. Can we separate the north pole and south pole? North pole and south pole? Can we separate north pole and south pole? Hmm?
No, sir.
I didn't get.
We cannot.
We cannot separate north pole and south pole, right? If this is called, how many poles are in this magnet? This is north pole, this is south pole. So it has two poles, right? Two poles. In this case, we see this have only one poles, that is monopoles, mono or one pole, right? So a magnet cannot be broken into monopole, right? If we get a magnet that has only one pole, a lot of physical quantity or definition will change. What the point? There in number of mathematical equation in physics will get changed. So monopole doesn't exist. Does not exist. We have only dipoles. Di means two or two poles. Clear?
Yes, sir.
Yes, sir.
So if what should we do now? Just bring some iron fillings. Okay, pieces of irons. I'm removing all these. Now bring some small pieces or powders of irons. Okay, iron or aluminum. Okay, so if you will bring iron, powders of iron, we will feel that this will be like this. Iron powders will stick to this magnet at two of its pole, at the end of its poles, right? So what does this mean? Have you did anywhere in experiments or in your daily life? Have you played with magnets?
Yes, sir.
So did you see any such type of feature there?
Yes.
So this is called the magnetic pole strength. Okay. So if the magnet has original length this, let me. This is called the geometrical length. If you will measure from this part to this part, this will be the geometrical length. Magnet's geometrical length. Geometrical length. That is the actual length of magnet. Yeah, actual length. Actual length. Actual length of magnet. So you will see that iron powders are not stick at the edge of it, but bit inside the edge. If you will see, you will find the center is bit inside the magnet. Let me show you one figure from your book only. It will be a bit clear. Have you seen such figure anywhere in your life?
No, sir.
So
Yes, sir.
the geometrical length of a magnet is different from the is pole strength. So pole strength, this will be, suppose this D, this is the pole strength. It's not at the edge. If you will grow this, you will find the center within inside. So these are the properties of magnets. Can we destroy natural magnets? Can we destroy magnets?
No.
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 No and yeah, both.
No, sir.
No and yes, both. You both said no. No, any of you said yes.
No,
Sir.
sir. We
No,
both said
sir.
no.
We cannot destroy the magnet. Even the tiny pieces of magnet will give some magnetic properties. But in some cases, if you will heat it or burn it, then it will be lost. If you are breaking it with hammer, even the tiny piece will give you the magnetic property. But when you are burning it, it will lost. Okay. We had a lot of uh, intro. So is intro is good for you?
Yes.
Yes, sir.
Now, going forward, we studied about the natural magnets. We can have artificial magnets as well, or man-made, rather I will say man-made. So there was very famous experiment is that I won't tell you, but I will ask. Suppose this is an electric wire connected with battery or circuit. Have you seen a magnetic needle? Have you
Yes.
seen magnetic needle? Now, just I'm asking, what will happen if you will bring this magnetic needle near the current carrying conducting wire? Question is clear?
Yes, sir.
What will happen?
The needle will be shaking.
Yeah, needle will be shaking. Okay, because there is electrons flowing. So this is what? Electricity. Electricity. Electron flows, it means there is electricity and there is magnet. So this is magnetic field over there. There is magnet, so it is magnetic field. Because of electricity, there will be electric field. It was the chamatkar or miracle of that time when Oersted found that when we bring a magnetic needle near the current conduct carrying wire, the needle gets deflected. Deflected. This is called the Oersted effect. And this type of arrangement you might have seen. Actually, I was not aware that we will be starting a new chapter today. So I couldn't make the, what can I say, slides. Okay, so it may this because of that. I'm first drawing the graph by hands and I'm showing you through the books. Clear? This was the current carrying wire, what I just drawn. And we found that this magnetic needle is getting deflected. So this is the combined phenomena, COMBINED, combined phenomena called electromagnetic effect. Electro plus magnetic effects. Effect, EFECT effect, right? This is called electromagnetic effect. And you won't believe, or you have to see that this changed dramatically the concept in physics. So what will be the direction of deflection? How the current will be deflecting?
Magnetic field.
Magnetic effects. Yeah. This is called the electromagnetic effect. And this was given by Oersted, I think, right? Oersted. It was the scientist name. Scientist. Did you get the meaning?
Yes, sir.
Oh, that's good. So what is actually, it is really a good, what can I say, horizon changing discovery. This totally changed the horizon of magnetic phenomena. Earlier, it was thought that magnetic field, magnets and electric field, current electricity, current electricity, city are different thing, different things, different things. But this experiment unified electro electromagnetic field together. Clear?
Yes, sir.
So you will read. I know you are not getting the essence and meaning of this revolutionary discovery. Okay, it's hard to understand now. It's look very simple, na? We bring a magnetic compass through the current carrying wire, and magnets get deflected. So it seems it's okay, no big deal. But it was the biggest deal of that century. So further moving, we can make electromagnets as well. Electromagnets as well. What are the use of these magnets? And these are the temporary magnets. Temporary magnets. Natural magnets are permanent magnets, right? But what we create in our labs, that called temporary magnets. Clear? So these electromagnets, when we switch the current, the magnet will be, the time we switch the current, the magnetic field will be generated, magnetic field will be generated, and that will be used to hold heavy metallic object. Heavy metallic objects. Clear? This is one of the use. I think there's no much to. There is one more concept. I think for the natural magnets, natural magnets called magnetic field lines. Magnetic field lines. Magnetic field lines. Read, my writing is okay.
Yes, sir.
Yes, sir.
You can see. So when we will see, where's my pen? I'm holding it. So this is North Pole and this is South Pole. So magnetic field of line. Have you heard about this word, magnetic fields of line? Have you heard about magnetic fields of line? Any of you? So magnetic fields of line will first property. This is North Pole and this is South Pole. This is pole strength. So it will be like from north to south, always. North to south. Clear? From north to south. And you will see as well that magnetic field line. It crossed over here now. So magnetic field lines never cross each other. Again, it is from north to south. This never cross each other. So actually, magnetic field of line shows the magnetic strength. Clear?
Yes, sir.
So if you will see in your books, you will find the structure like this. See, it generates from North Pole and it's at South Pole. So you see that there is not a single magnetic line crosses each other. Clear? So magnetic field lines, that second property is magnetic field lines, magnetic field lines never CROSSES crosses each other. Clear? Any issue?
No, sir.
It's just, I think, is this chapter is only based on some information. Do we have any numerical? Let me see.
The theory chapter, sir.
Yeah, basically it's theory chapters. So we are left with one more concept. Let me show you. I asked one question, how the field will deflect. So I think there is the answer. So see, the current is flowing toward this direction. Okay, so we have a magnetic needle and magnetic needle, this corresponding to, we have north, south and east. So when current is going in positive direction, we see that the north pole is being deflected. When current is going in this direction, we see that north pole is in this direction being deflected. So simple electric circuit in which a straight copper wire is placed parallel to and over a compass needle, the deflection in electric field become opposite when the direction of current is reversed. So suppose, did you get the meaning of it? Suppose, suppose this wire, the current is going in this direction, right? This is the direction of current. So I have kept a magnetic needle. So if the deflection is in the needle is in this direction, the lower direction, if we will change the direction of current, the direction of deflection will also change. Got the point?
Yes, sir.
So this was some of the points we made for this class. If you have any doubt till now, we'll do it again. Okay, I think we will collect some material from some different books and we will study in the next class. One more thing, one more important thing is So suppose this is the magnetic field lines, okay? This is the current carrying wire, okay? If this is the current carrying wire, so what will be the, if we will hold this wire, if the finger points in the direction of electric current, so this curling of this finger will give you the circulation of magnetic field. Okay, so see over here. So here the direction of current is this wall. First, I'll show the right direction. If we are hold direction of current, right hand thumb rule, right hand thumb rule. So take the pen, take the pen in right hand, okay, and nib at the upper direction. So just hold it. If the direction of current is along the thumb, then this circulation will give you the direction of magnetic field. Because a current carrying wire generate magnetic fields. So in magnetic field, if the direction is in this world, the curling of finger will give you the direction of magnetic field. Clear? Did you get this
Yes.
concept?
Yes, sir.
So for today, this will be enough for the day. Okay. We will start the rest of the concept in the next week. Next class, right? So now ask, did you get all of the information? Any confusion? Any question?
No, sir.
Okay. So what can you give me a little summary, starting with Tejasvi?
Yes, sir. We know that the metallic effects, like the magnets, are made of natural materials,
Hmm.
and some of them are man-made, and
Mhm.
we also make them in labs.
Mhm. Yes.
Uh,
So
we cannot like destroy the magnet, but on heating we can destroy it.
mhm. Okay. So how many poles are in magnets?
Two magnets, south
So
and north.
okay. So can we have the only one pole magnets or monopole?
Sorry, sir.
Can we have only one pole in magnet?
No, sir, we cannot.
Okay. So Govita, what we mean by the magnetic geometric physical length of magnets or the pole strength of magnet? What I said, what we mean by the magnetic field lines.
Magnetic field lines result in formation of closed loops.
Closed loops, right? So what is the direction of those magnetic field lines?
So can you please repeat the question?
Uh, what is the direction of magnetic field lines? What is the direction of magnetic field lines?
South pole to north pole.
No, north to south.
Oh,
Does
North
the
to
Yeah. Does the magnetic field lines cross each other?
No.
Okay. So what is the Oersted effect?
Sir,
Yeah.
can you repeat the question?
What is Oersted effect?
Keeping a magnetic needle on an electric current passing through a metallic conductor.
Yes. Current carrying metallic conductor. So what happens?
The magnetic needle gets deflected.
The magnetic needles
The needle get
deflected. So this effect called electromagnetic effects. Okay. Because this unifies the electricity, because the current carrying in a conductor is purely different phenomena, and magnetic needles is a different phenomena. So when these two are bring together, we see the one is affecting other, right? So this is the electromagnetic phenomena. Clear?
yes, sir.
Okay. Any questions?
No, sir.
Okay,
sir.
we'll meet next week with some more. We are left with some concept over here, so we will be doing in next week. Clear?
Yes.
Yes, sir.
Okay, bye.
Thank you, sir.
Bye, sir. Thank you, sir.
Most welcome.